So I've been working here at Google for about a year and a few months. I started last summer. Yeah, I'm not quite that tall. I came over here as a professor at Carnegie Mellon University. I'm now starting up like a small research group doing machine learning, of course, and NLP sorts of things. And I'm just going to give you a little flavor of like one of the projects going on in my group. I won't be around too much this afternoon. I'll be back for a little while around happy hour if you want to talk about it. But here's a problem, okay? So this actually looks a little bit different than I thought it would. But this project is called Neural Query Language, NQL, and it's all about queries on a knowledge graph, okay? But doing them in a way that's completely differentiable, okay? And doing it inside TensorFlow. So here's the motivating task. So here are a couple of examples of this. So from a paper. So here's a question: which states does the Mississippi run through? And the way to answer that is with some sort of like query against a database or knowledge base, okay? Or another one is in Denver, what kind of ground transportation is there from the airport to downtown? Again, sort of the same kind of thing. There's a natural language question, and you want to have some sort of structured query language, okay? So this is a problem. People don't know what's in their databases. They don't know how to ask questions. So, using natural language to access that kind of makes sense. A slightly harder problem as a learning task is if you're given the question and the correct answer without being given sort of the underlying database query. All right. So here, X, the input, is a natural language question. Y is a knowledge graph query. Here, Y is just the answers you want to get. So there are many cases where this sort of data is a little bit easier to obtain, but it's harder to use. Okay, so the problem here is there's some missing step here, which is what's the query going to be against the knowledge graph, and that's hidden. That's a latent variable. Okay, so somehow you have to deal with that. So how do you deal with that? So the idea behind NQL is the following. Okay, what we're going to do is we're going to have a structured query that produces a set of knowledge graph entities. Okay, and we're going to do this with an encoder-decoder strategy. Okay, so you're going to start out by encoding the natural language query, and then you run it through a decoder process, which gives you something like a structured query, and then you execute it on the knowledge graph. Okay, so this is kind of the standard thing. How do you deal with the fact that this is like latent, so you don't have any explicit training data for that? All right, so the basic idea is what we're going to do is we're going to turn this execution against the knowledge graph into something that's also part of the neural network. Okay, so the execution will be something that's also done in the neural network, and then when you look at your target answers, you can look at those answers and you can compare them with what the neural network actually provided. So here there's a mistake. It actually gave you the wrong relation. It's like defines border instead of runs through. Okay, so this is the answers. They're not right. I highlighted the differences here. Okay, so there's going to be some loss on that answer. And what you want is you want to be able to propagate that loss all the way back to the things that actually made the mistake. So here we're going to propagate the loss back through the execution of the query against the knowledge graph, okay, and figure out what went wrong, what sort of errors were made in those decoder-encoder steps. So we can use this indirect data, it's just the answers, to train the encoder-decoder pipeline. This is the idea behind NQL. We want to be able to execute a structured query, generate a set of knowledge base entities. We want to do it in a way that's completely differentiable, so you can take the loss and you could push it through the knowledge graph back to whatever components that you need to use that semantic parsing task. All right. So there's a whole system that is a query language for knowledge graphs. It's part of TensorFlow. It's now been open sourced, so you can sort of try it out and use it no matter where you are. And here's some examples. So these are basically the simplest type of expression is you're just basically saying this is a singleton set. So this is a set of one element. Here's the name of the element, and here's the type. Okay, so Queen Vic and Henry VIII are expressions now in this language, and when you evaluate them, and I guess in TensorFlow 2.0 you can do this a little bit more easily, using eager execution. But when you evaluate them, you'll get back the set of things. So you notice the set here, actually every element of the set has a number. So all the things in the set are soft. That's kind of important. Here are a few more expressions. So we've got Henry VIII, that's a singleton set. And then I apply a relation. So this is basically finding all the entities in the knowledge graph that are related to Henry VIII by the wife property. Okay, so if you know your history, he had 6 wives. And Henry VI, of course, had 8 wives. I think that's right. Here's another more complicated expression. We've got the wives of Henry VIII, and I want to intersect those with the daughters of Ferdinand V. Okay, so if he was married to one of Ferdinand's daughters, then that would be like a non-empty set. Otherwise, it would be an empty set. Turns out there's a singleton set. It's one person. Or here's another one. These are all the sons and daughters of Queen Victoria. So these are the sorts of operations you can do. You can basically sort of follow chains of properties. You can do unions and intersections. And you can compose those so you can construct relatively complex queries. And the important things about these is each one of these expressions is actually a wrapper around a TensorFlow compute graph. Okay, and it's fully differentiable, right? So you can send a loss through it. You can drop them anywhere into a neural model, so you can use knowledge graph information wherever you want. Okay, and everything's also extended to sort of a soft probabilistic setting. So all the sets of entities are weighted sets. Okay, here the weights are all 1.0, but that doesn't have to be the case. All right, what's really constructed here is a vector representation of those sets. So you know, when I'm printing things out like here, okay, I'm giving you strings that are associated with numbers. Under the hood, it's really just a kind of TensorFlow representation. So the eval is just a little bit of syntactic sugar. Okay. Here's another thing you can do, which is less common in a query language. So you can also define a set of relations. Okay, so here I've defined a set of relations which are nuclear family relations, and I've got 2 singleton elements, the wife relation and the husband relation, and I put them together and I call it the spouse relation. So I can follow any one of those spouse relations. So I can find out whoever you're married to, right? So this is a little bit more, you know, I guess say less, you know, patriarchal, like, you know, gender normative, right? You can just say find someone's spouse rather than specifying husband or wife. So that's kind of nice from a diversity point of view, but it's also really practical from a machine learning point of view, because a very typical thing is to do this semantic parsing thing, you've got to guess. The machine learning system has got to guess not only what the structure of the query is. So in this case, the query is basically starting with some object, the Mississippi River, and following one relation. So it's a simple kind of query. Okay, but it's also got to figure out what are the constants in that query, okay? And those constants can be relations. So here we've got the relation traverse state. So that's something you've got to predict, okay? So the way you'd actually do that in NQL, what the semantic parser would look like for this, if all you cared about was sort of like these single relation queries, is you'd first construct your kind of seed set, which would be Mississippi in this case, and that's some function of the query. All right, and you could use any differentiable function you want. So whatever you want, you know, you could use BERT, you could use encoder-decoder strategies with transformers or LSTM, whatever you want to do. Okay, and you'd also pull out the relations, and then you'd construct a query where all those things are potentially variables. So you'd execute that and get the answer. Okay, and if you had if you were working in a setting where you also had more complex queries, so here is one where you're following 2 relations, right? Then you've got to construct a few more constants, right? You have to construct, you know, the constant for the seed set here, and here we got to construct 2 relations, okay? And then you got to choose which one of those types of things to follow, which one of those patterns to use, but you can just sort of disjoin them and let the learning system sort out what you want to do. So it's relatively simple to do this kind of semantic parsing in an encoder-decoder framework. Here's some numbers. These are on the left-hand side. This is varying the number of entities. Okay, so we're going to, from a small knowledge base to one that has about 1 million entities. Okay, so you see things get slower. That's queries per second, so it's getting slower. The other one is like varying the number of relations, so it's going to between a handful of relations and about 1,000 relations. Okay, and that straight line on the top is sort of the implementation of NQL. These other ones are kind of baseline methods. Okay, and I guess the punchline is the graph on the right, where this is the speed up over sort of the baseline methods, right? So depending on which baseline you use, it's either 50x or about 12,000x, so like 4 orders of magnitude faster than that. So this is basically just doing kind of clever tricks with sparse matrices. And here's some other numbers. So this is looking at accuracy of systems that do this end-to-end semantic parsing on a few different problems. The big one is this WebQ SP thing, which is about, if I remember correctly, about 40-something million triples in the knowledge graph, and on the order of like 10 or 15 million entities. The one that has more complex questions is this meta QA, and there's a synthetic one we developed. And the models for all these, the decoder models look like this. So that's one for Web Questions SP, that's the one for meta QA, that's the one for the grid. So they're very simple. Because this model is relatively straightforward to modify, this is like sort of like one extra line of code to handle one additional property that that this very simple model didn't have. So that's basically doing exclusions, okay? And that gets you sort of to the state of the art for these meta QA tasks. So this is basically all I wanted to say. So just kind of to give you a quick wrap up. So what NQL is it's a language that lets you query a knowledge graph in a differentiable way. It's relatively expressive. You can drop it into a model anywhere you want. So the model, the implementation we're using now currently scales to around 10 million triples, 1 million entities, okay, and that's running on a set of multiple GPUs. Those were experiments with using 4 GPUs on one machine. So you can go a little bit further than that. We're working on ways to scale it up even more. This makes these very, very simple models competitive on some pretty hard knowledge-based type tasks. We talked about semantic parsing from these sets, these denotations, and also the knowledge-based completion is something else we've looked at. And here's some follow-up points. All right, so I got a couple of minutes for questions.
Actually, we're going to bring our next lightning talk speaker up, and then we'll have both of you up for questions.
Okay, cool. All right.